Good morning, guys. Is that, that's not you guys. No, that's you guys. Okay. So, is it just Austin? Oh no. Oh, there you guys are. Okay, cool. So today we're going to continue our talk about polar coordinates. There's kind of two things that we need to work with a little bit in order to have all the good stuff from polar coordinates. There's quite a few things you can do. You can talk about tangents, you can talk about arc length, you can do all the things that you can do in any other coordinate setting in the polar coordinate setting. But really, there's the two things that are fun or interesting or worth doing because they get better in the polar coordinate system are certain kinds of graphing and certain area problems. But before we actually get to solving those, we're going to need a little bit more background with the polar coordinate system. We're going to need to get a little bit more comfy. Working in that setting at all. So I am going to assemble some paper here. And we'll just start playing around with some basic examples. I guess before I start picking examples, if there's anything in the homework that you guys have gotten to so far that you wanted to take a look at, I'd be happy to. We haven't really gotten very far in terms of the discussion here yet, so I don't have any particular feelings about any of those problems yet. I understand.
Will you be giving us the take-home exam this Friday?
This Thursday, yeah.
So tomorrow. Okay. And when will it be due?
The final.
Okay.
Yeah, so for you guys, that is, oh, sweet, here's the good stuff. Yeah, let's take a look and remind ourselves. I think your final is the 28th, but I need to check.
It's the 27th.
27th. Let me just verify that so I can be 100% confident with it. Yeah, okay, the 27th. So, yep, so I will give you guys the take home tomorrow, which is the last day of class for us this semester, right? And then you guys will hand it in. Let's see, Tuesday, that feels a little, oh no, I guess the 23rd, that's not too bad. Yep, and you'll hand that in on the 27th. And it's going to be something where you can, you'll obviously, if you can print and write on the paper if you want, or you can just write out your solutions on scratch paper and then scan and upload them to Canvas. But yeah, I'll accept those for the whole day during the 27th. And that'll of course also be the day of your final exam, which you'll do online in the same way that we did exam 3. Okay.
Do we still need like a nice webcam in order to do the exam?
A nice webcam. I don't know exactly what the requirements for honor lock are. But since, let's see. Well, so here, we've got a second now, right? Let me pull out of this here and back to another view. You guys know how to use the response things on here? If you do not have a webcam that you could use for honor lock or proctor U, go ahead and give me some sort of signal here. So how many would have trouble if we tried to use that? Because the alternative is the WebAssign lockdown browser that we used for exam 3. Does everybody have a webcam that they could use for HonorLock or ProctorU? Cool. I'm doing my third exam with HonorLock today. The first two I did last week and did not go well at all. A lot of the students had a very hard time following the instructions necessary to verify their identity, and then when they ran into those troubles, they had a very hard time getting to talk to somebody in the live chat. So depending on how things go today, I am deciding whether or not I want to fuck with HonorLock at all moving forwards. The place I'm in from last Friday when I did those last two tests is that no, I don't, and then we would use the lockdown browser just like we did for exam 3. But if things go a little bit more smoothly today and I get good feedback about HonorLock and their support mechanisms getting better, then I would be inclined to want to use HonorLock because I know it's a more thorough proctoring system. And given that, yes, you would need a webcam. I don't know how high quality it has to be. I've seen people use HonorLock with built-in webcams from several years old laptops. But I've also heard of HonorLock being a little bit fiddly about the quality of the ID photo that you present them. So I don't have any reason to believe that we couldn't. Is that why you were asking? Like, are you concerned that the quality of the webcam you have access to isn't sufficient, or what was
Yeah, my webcam's like pretty old, and its quality is kind of bad. So I was wondering if I needed to pick up a new one.
I see. I don't believe you will need to pick up a new one. If we do use HonorLock, I'll go ahead and just for shits and giggles in Canvas today, I'll open up an HonorLock practice quiz, so you can go in and see if it allows you to run through the verification mechanism. And if it does give you any trouble, let me know. But I don't expect that it will. So we do have a finite amount of time. I mean, it's not connected. This damn thing. Well. All right. So let's try rebooting this, and then we will talk about graphing some curves in polar coordinates, and maybe even get to look at some area problems. Okay. So in this week's homework, I went fairly gentle. I didn't drop any of the really challenging area problems on you or anything like that, because I know the situation we're in is not ideal. The last thing that we looked at was just the basic definition of polar coordinates and a little bit how to go back and forth. So if I have this Cartesian point, x comma y, so this is x on the x-axis, this is y on the y-axis. I can also think of that as r comma theta, where r is the length of that hypotenuse and theta is the angle subtended.
I don't think the camera is working.
Weird. Back through its autofocus routine. There we go. So, all right. And to go back and forth from one to the other, we had this little dict.
It's still on you instead of the,
Oh, really?
yeah.
That's better?
Yeah.
Okay, sorry, thank you. Having trouble with this dot cam lately. Okay. So this is more or less where we left off. If you have a point, Cartesian point, x comma y, and you want to move from that point into polar coordinates, so you want to find the r and the theta associated with that x and y, usually we would use these two guys. And if you have a point in polar coordinates, r comma theta, and you want to find the x and y, so you want to go from polar back to Cartesian, usually you would use these two guys. But these are the four little relationships, the key, the dictionary, whatever, that lets you go back and forth between Cartesian and polar coordinates, between the x, y, and the r theta. The tendency to write r first is what your book does, and it's what WebAssign is going to require you to do. It's a little bit unfortunate because normally we like to think of, when we think of graphing functions in this setting, we like to think of theta as the independent variable and r as the dependent variable. But nevertheless, your book and the convention is to write r first and then theta. One reason for that is because when you're finding this point, when you're using the polar coordinate system to get where you're trying to go, rather than thinking of rotating first and then walking out some distance, many people choose to think of going out along the horizontal axis, which they call the polar axis, instead of the x-axis in the polar coordinate system. So you go out and you pick a radius, and then you rotate up until you get to your point. But you can think of it either way. And in my mind, I've actually always thought of it as rotate theta and then walk out r. But you can also walk out r along the polar axis and then rotate around on that circle until you get to your point. Either way is okay. On Monday, we saw how to go back and forth with a pair of points, but what we haven't addressed yet is how to handle or how to understand what to do with a negative r, because we think of r as a distance most naturally. So that's what I would like to talk about first. So what do we do with r values that are less than 0? Well, it's a question that has a straightforward answer. We reflect through the origin. So I can draw a few points over here, like maybe this guy as r comma theta equal to 2 comma pi over 4. If I reflect him straight through the origin to this point over here, one way of describing the point down here would be to say he has r comma theta equal to negative 2 comma pi over 4. So both of those points have the same theta, which is a little bit odd. Because the point down there in quadrant 3 does not appear to have been arrived at by rotating by pi over 4. One way to think about this is to say, okay, well, to get to this point, I come out here along the polar axis to r equals 2, and then I rotated up by pi over 4. Similarly, I could think about this guy by saying I came out along the polar axis to negative 2, and then rotated pi over 4 in the positive direction. That's one way to say it. The other way to say it is you reflect through the origin. whichever one you are most comfortable with, I encourage you to stick with. I usually think of it as reflecting through the origin, because when we think about the polar coordinate system, the polar axis usually only extends off to the right. But either one is okay, and I've had a number of students who really struggled with the reflect to the origin thing very much enjoy this perspective. So this is -2 comma pi over 4, and this is +2 comma pi over 4. The geometric relationship between the two is that they're symmetric about the origin. If you wanted to graph this, if you were given this right away, what I would do is graph this, or at least think about this, and then reflect him through the origin. But the alternative is to walk out on the opposite direction. You could walk out along the negative horizontal axis 2 units, and then rotate in the normal counterclockwise positive oriented direction by pi over 4. What this means, and we mentioned this last time, but we didn't do many calculations, is that polar coordinates are not unique. If you give me a particular point, I can come up with many sets of polar coordinates that get you to that point. And they're not unique in more than one way. Another way I could describe this point down here, the -2 comma pi over 4 point, is as +2 comma 5 pi over 4. So there's kind of two ways that polar points polar coordinates are not unique. And this is kind of the only shitty thing in the polar coordinate system. The Cartesian coordinate system, if you give me an ordered pair x comma y, that ordered pair indicates one point, and that point can only be indicated by that ordered pair. But in the polar setting, there are two ways that polar coordinates are not unique. The point r comma theta is going to be the same as the point r comma theta plus 2 pi. Is going to be the same as the point r comma theta minus 2 pi, and so on. Right, so there's the modulo 2 pi thing, where you can spin all the way around the circle and come back to that same point. But also, there's this thing with -r. So I could have r comma theta, and that's going to be the same as -r comma, well, if I wanted to write this guy with a negative radius, I could call him -2 comma, how far around do I have to walk? Well, it'd be pi over 4 plus this, and this is pi. So I could say theta plus pi, or -r comma theta minus pi. And then you could also do the 2 pi thing to any of those. So polar points are non-unique, and every point in the plane has kind of two infinite families of polar representations, one where the r's are positive and one where the r's are negative. You can get rid of this. If you require r to be positive and theta to come from the interval 0 to 2 pi, then polar coordinates do become unique. And so that's an easy fix. And that's the fix that you'll find people use when you solve problems in physics and chemistry and electrical engineering using the polar coordinate system. When you talk about things like phase space in circuits, this will be the fix for it. They'll just say r has to be positive and theta has to come from the interval 0 to 2 pi. But for us, when we're dealing with these things as purely mathematical objects, we have to take this non-uniqueness into account. And especially this business when r is negative is going to be important when it comes to graphing polar curves. And that's the next thing I'd like to do with you guys. Maybe one quick example here where we come up with several representations of a point. Graph some curves. So let's find 3 ways to represent the Cartesian point. square root of 3, let's say 1 in polar coordinates. Right, so I'm going to start by drawing the point. So I come out here to negative root 3, and up here to 1. There she is. All right, there's my point. And so the question is, can I find the polar coordinates, or can I find some polar coordinates for that point? Why am I getting hit with all these things right now? Okay, none of it's for us. All right. So what do? How do I find some polar coordinates?
You have to calculate r and theta.
Yeah, exactly. So r squared is always x squared plus y squared. So in this case, r squared is the square root of negative square root of 3 squared plus 1 squared. This is 3, this is 1, this is 4, which means r is either 2 or negative 2. So we can come up with polar coordinates where r is negative 2 that get you to this point, and we could also come up with polar coordinates where r is positive 2 that get you to this point. Let's do both. If I choose to think of r as being 2, and I walk out along my polar axis to the radius 2, how far around do I have to spin before I get to P? How do we find theta? Well, the tangent of theta is always y over x, right? So here, tan theta, y is 1, x is negative square root of 3, so it's negative 1 over the square root of 3. Can anybody tell me a theta value over there in quadrant 2 so that the tangent of that theta is 1 over the square root of 3? Think about your unit circle. I know it might have been a little while since you've had to do these trig calculations. I apologize if I'm impatient. I did this recently with my trig class, and I beat this shit into them so hard that their unit circle recollections are fairly quick. Think about dividing the top and bottom both by 2. Then this would be 1/2 over negative root 3 over 2. What point on your unit circle has y coordinate 1/2 and x coordinate negative root 3 over 2?
This is 2 pi over 3.
No, not quite. If I swapped them around, that would be 2 pi over 3. But the other one over there in quadrant 2, the one that's closer to the horizontal axis?
5 pi over 6.
Yeah. So one set of polar coordinates that works the point P is represented by the polar coordinates r theta, where r is 2 and theta is 5 pi over 6. And this is the most natural representation of that point because this is the one that has r positive and also has theta between 0 and 2 pi. Hey, Hammy. Sorry, my dog's acting very weird this morning. Yeah, I don't know. He's dealing with some pain in his back leg. I've been worried about him. It's nice to see you, bud. But that's not the only way to represent this point, right? There's infinitely many ways to represent this point in polar coordinates, and I could get one infinite family from this point, from this set of coordinates, just by adding multiples of 2 pi, right? So Another representation with r positive is r comma theta, where r is 2, and theta is 5 pi over 6 plus 2 pi. 2 pi is 12 pi over 6. 12 pi plus 5 pi is 17 pi, so that's 17 pi over 6. Yeah, here we just added 2 pi to theta. So that's one more representation. And I could come up with lots more using that same trick, right? Just add 2 pi again, add 2 pi again, add 2 pi again, or subtract 2 pi, subtract 2 pi, subtract 2 pi. You know, every time I add or subtract 2 pi, I just spin around the circle again and land back at that point. What about a representation with r less than 0? Well, I know from the very first calculation I did that r would have to be -2. Right, the distance from the origin to that point, or the distance from the pole to that point, is definitely still 2. So the only choices for r have to be +2 or -2. We got that out of our little Pythagorean relationship at the top. But how do I find theta here? If I walked out -1, -2, how do I get from this location on the polar axis to P? Or if you like, I can think of P as being reflected through the origin from what point? Thoughts on that? So if I come out here to -2 along my horizontal axis, and I wanted to rotate all the way around in the positive direction to get to P, I know that this little angle here is pi over 6. So this would be all the way around minus pi over 6, which is 11 pi over 6. So I could also say P could be represented as r comma theta, where r is -2 and theta is 11 pi over 6. And there's one other kind of sneaky way to do this. I could say r is -2 and theta is negative pi over 6, right? Instead of coming out here and rotating around in the positive direction, I could come out here and then rotate backwards, the negative direction. And both of these would be valid representations of that point. The next thing we're going to do is graph some functions in the polar coordinate setting, but in order to do that, we do really have to be comfortable with this -r stuff. So I want to take a minute and pause here and make sure we answer any questions that you guys have, concerns. Anything like that?
So when you're finding r, you always use the r squared is equal to x squared plus y squared.
That would be my recommendation, yeah. Now that'll always have two solutions, right? As a function of r, that is quadratic. So there's always going to be two solutions, a positive one and a negative one. But yes, yeah, I would always use the r squared equals x squared plus y squared relationship to find r. Come on. Sweet boy. Any other questions there? Everything else feels okay? So the first few problems in your homework do have you doing this sort of stuff. I think the first problem or two after the basic definition and like find the point questions are going to be give me some other representations, and they'll have some domains for r and theta specified. So first they'll ask for one where r is positive and theta is between 0 and 2 pi. That's always the most important one to find. But then some of them also do ask you to find polar coordinates where r is negative. So it is crucial for more than one reason that you're comfy, especially with this bottom box thing. No questions on how we got these theta values associated with r equals -2? Just for shits and giggles, and then we'll move over to graphing. All right, let's graph these 3 points. The first one, P1 there is -1 comma pi over 2. So let's draw a coordinate plane. The origin in the polar setting is often called the pole, and the horizontal axis pointing out to the right is called the polar axis. So if you hear me refer to those things as such, that's where they are. That's what they are. If I mark this as 1 and this as 2 along my polar axis, then I could get to the point -1 comma pi over 2 by first going to the point +1 comma pi over 2, which is up here, and then reflecting through the origin. So I suspect that that point is over here. The other way to think about it is to go out in the negative direction along the polar axis and then rotate in the positive orientation by pi over 2. So yeah, P1 is down here. And if you want, one way to think about how we get there is by also thinking about this point, 1 comma pi over 2. That's the polar point up there, 1 comma pi over 2, and then I reflect him through the pole to get down there to P1 or through the origin. But I have found that more people seem to like they go out a negative direction and then rotate. Okay, what about 2 comma negative pi over 3? I would walk out here, 1, 2, and rotate an angle of negative pi over 3. If I rotated the angle positive pi over 3, that would put me up here. If I rotate in the other direction to negative pi over 3, that will put me down here. So this is P2. I walk out 2, and then I rotate negative pi over 3. So I walk out 2 and then rotate negative pi over 3. And then finally -2 comma negative pi over 3. Let's see, so here's walking out to -2 along my polar axis. Rotating an angle of positive pi over 3 would bring me down here, right? Because when we rotate through a positive angle, we're always moving counterclockwise. But if I come out to -2 and then I rotate negative pi over 3, that's going to bring me up here. So this right here is the point P3. Are you feeling it, Mr. Krabs? So that's how I get from the polar axis to P3. I walk out to -2 because r is -2, and then I rotate in the opposite orientation from a normal angle by pi over 3 to get to P1, I walked out to -1 and then rotated in the positive orientation. Oh shit. Okay. Here and then rotated in the positive orientation by pi/2. And to get to P2, I walked out to 2 and rotated in the negative orientation by 60 degrees.
For P3, could you have just gone out like to +2, rotated -pi/3, and then just reflected it through the?
Yep. Yeah, so to get to P3, you could have reflected P2 through the origin, right? Did I say that right? Yeah, to get to P3, you could have reflected P2 through the origin. The relationship between P2 and P3 is that they're the same point. It's just that R has gone from being positive to negative. So yeah, you could have walked out here, then walked down here, and that would get you to the point 2, -pi/3. And then to get to the kind of sister point where R is -2, so -2, pi/3, you reflect him through the origin to get up here. Yeah, good question. Other questions on this? Questions on graphing in polar coordinates, like plotting one point at a time, or swapping from polar to Cartesian coordinates, or Cartesian to polar coordinates? Okay, if anything does come to mind, don't hesitate to shout out. So the real fun begins when we start asking, what about graphing functions in polar coordinates? And I want to look at a couple of kind of basic functions first, like constant functions. And then we will extend that to thinking about more and more functions. It turns out the types of functions we like to graph in the polar coordinate system are functions that are either very simple, constants, or functions that exhibit some sort of rotational symmetry. So those are functions whose origins are geometric in nature, like sine and cosine, and variations on those. The first couple that I would like to look at, though, are some constant functions. Remember in the Cartesian coordinate system, the two constants, like y equals a constant, y equals 1, y equals 5, y equals -2, those are all horizontal lines. And the others, x equals 1, x equals 5, x equals -2, those are all vertical lines. So let's see here. What does the graph theta equals c look like, where c is a constant? So maybe a good first example here would be looking at theta equals pi/4. You could make a table if you wanted to, a bunch of r's and thetas. But since this is a constant function, theta is always pi/4. So no matter what radius you're looking at, theta is always pi/4, which means you're going to be along this line. Some examples of points that would be along this line, like 2, pi/4. 1, pi/4. And these are polar points, remember, so these are r, theta. -1, pi/4. The graph here is all of the polar points whose theta coordinate is pi over 4. We could look at the constant theta equals, how about negative pi over 6? So again, you could make a table of values and then plot these points one at a time, but I think we are in this class sophisticated enough to move a little faster than that. If I take the point negative, or 1 comma negative pi over 6, that means I would come out here to 1 and come down pi over 6. Negative pi over 6, sorry, yeah, come down by pi over 6. Or I could come out to 2 comma negative pi over 6. Or I could come out to negative 1 comma negative pi over 6. And so on. So modulo my bad art, you'll see that these are all straight lines through the origin. Well, so theta equals a constant is always going to be a straight line through the origin, or a ray, right? A ray emanating from the pole. Because that's what the collection of all polar points r comma theta look like when theta is a fixed constant. Next family to look at is r equals a constant. If I take the equation r equals 1, what's the graph of that look like in the polar coordinate system? Well, some points that would be on that graph would be 1 comma 0, where r is 1 and theta is 0, and 1 comma pi over 4, or sorry, pi over 2, where r is 1 and theta is pi over 2, or 1 comma pi, or 1 comma 3 pi over 2. This is going to be the unit circle. There's lots of other points on here, right? Like here's the polar point 1 comma pi over 4. Here's the polar point 1 comma 5 pi over 4. So if you take the collection of all the points in the polar coordinate system whose r coordinate is 1, that means you're always going to be on the circle of radius 1. So this is the unit circle. And I want to take a second to appreciate how damn nice that is. The unit circle in Cartesian coordinates has equation x squared plus y squared equals 1 squared, or 1. So that's the same as saying y equals the square root of 1 minus x squared, which is fairly complicated. To do things like integrate that in the Cartesian coordinate system required trig sub, right? Remember, that was one of the first big hurdles we had to get over in this class, was just finding the area of a circle using integration. It wasn't an easy thing to do because the equation in the regular Cartesian coordinate system for a circle is not a nice equation. It's a fairly complicated thing. But here in the polar coordinate system, it's nice. It's so nice. It's a constant. That's fucking cool. And this kind of gives us a feel for the types of things that are nice to do in polar coordinates. The types of things that are nice to do, the types of functions that are nice to graph, are those who have a lot of radial symmetry, right? The circle is a perfectly radial symmetric object. So before I move too far down that path, what do you think the equation r equals 2 looks like? If I want to graph him in polar coordinates.
Is it just a bigger circle?
It is, yeah, it's a circle of radius 2 centered at the origin. All right, you can trust your intuition here. So if I mark this as 1 and this as 2, 1, 2. Yeah, here's the point, the polar point 2, 0. Up here is the polar point 2, pi over 2. Over here is the polar point 2, pi. Over here is the polar point 2, 3 pi over 2. And if you look at all of this together, it's just a bigger circle. It's just a circle of radius 2. So the takeaway, this is the takeaway here is that when you transform the plane from Cartesian x, y into polar r theta, horizontal lines become circles and vertical lines become rays through the origin. So the family of curves here, r equals c, is always a circle of radius c centered at the origin, and theta equals c is always a ray or line through the origin. So horizontal lines get wrapped up into circles, vertical lines get turned into rays. That's the idea. And kind of you can think about the whole polar coordinate transformation in terms of those two things. And that's why that polar coordinate graphing paper that I talked about last time, just like when you start graphing functions in the regular XY plane, you usually start with regular graph paper that has horizontal and vertical lines. And that's why the polar coordinate graphing paper has concentric circles and rays, because those are the constant functions. Make sense? So the first kind of new thing we might want to look at, let's look at one more. One more fun example. After you graph y equals 2, y equals 5, and x equals 1, and x equals -3, I think the first thing you graph in an algebra class is probably something like y equals x, right? Let's sketch r equals theta. So if r equals a constant is a circle of radius that constant, then r equals theta is trying to do something similar, but as theta increases, r increases as well. So let's find some points that are on this graph. When theta is 0, r is 0. So the point 0, 0 is on the graph there. Anytime r is 0, you're at the origin. If theta is pi over 4 radians, pi over 4 is a little bit smaller than 1. And so if I mark, say, here as 1, and here as 2, and here as 3 along my polar axis, then the radius pi over 4 is a little bit smaller than 1. It's like 3/4. So if I take that point and I rotate it up to pi over 4 radians, here's the point pi over 4, comma, pi over 4. Pi over 2 is closer to 3/2, right? So that would mean walking to about out here along my polar axis, and then I swing him up to pi over 2. So here's the polar point, pi over 2, comma, pi over 2. Pi is about here, and if I swing him all the way around, here is the polar point, pi, comma, pi. Can you tell what shape this is?
Is it a spiral?
It is. It's an Archimedean spiral. It's a spiral that we've seen before. So let me share full screen. So Desmos will graph things in polar coordinates. If you come over here and scroll down, down, conics, polar rows, polar conics, polar limison, polar logarithmic spiral. We can start with this. Why not? So this is not what we're looking at. We're looking at just this. And if I zoom in here, let's see, I can get rid of that. Yeah, there it is. It's our good old friend, the Archimedean spiral. We saw him when we talked about parametric equations, right? Now here we just had room to graph the very first little bit, right? Just really just this little from the origin out to here on my paper. But of course it does continue around. And you see it's that spiral that kind of grows at unit speed. Today is Wednesday, so we're gonna have to stop here for today. So tomorrow we're gonna look at graphing some more complicated functions. I encourage you to play around in Desmos. Try to push forwards a little bit if you can in the homework. The next example and the last example that I'd hope to go over with you guys today was graphing r equals cos theta. This is not terribly hard. You can get there by graphing cos theta in the regular Cartesian coordinate system, and then kind of translating that graph over one point at a time, thinking about increasing and where r is increasing and where r is decreasing. But you have to be careful about what you do when r is negative. So between theta equals pi over 2 and theta equals 3 pi over 2, the r values along this graph are negative. So this is the regular rectangular graph, r equals cos theta, right? This is your regular cosine wave. If you want to try to transfer this graph over into the polar coordinate system, I would say, okay, well, when theta is 0, r is 1. So I'm going to mark this as 1 along the polar axis, and I'm going to start out here. And then I just imagine letting theta start to rotate. And as theta starts to rotate, r is coming down. So I rotate up, but come in a little bit. I rotate up a little further, but I come in a little bit. I rotate a little further, but I come in a little bit. So now I'm like right here along this graph. And as theta gets closer to pi over 2, as my arm gets closer to being like this, my little dude's going to run all the way into the origin. So I end up here. And this little part of the graph corresponds to this part of the graph. But then as I rotate past pi over 2, where normally I would be drawing here, my r values are negative. So I'm going to have to take what I would draw over here and reflect it through the origin. That's going to end up doing this. I did post some videos, some Patrick JMT videos to your Canvas modules where he runs you through this procedure, and he does a very good job of it. If we look here under modules, not the parametric stuff, but the polar stuff, polar coordinate basics, polar graphing functions. Yeah, go ahead and take a look at this video. And see if you can't get comfy. And then tomorrow, we have a slightly longer period. It's going to be our last class. Holy shit, guys, it's almost over. You've done so well. I will show you how to graph a few more complicated functions in this polar coordinate setting, and then we'll talk about how to find areas. The area problem here is actually really nice, and that will be the end of our course. Also tomorrow, I will send out the take-home exam, which is the last test for this class. And you'll make sure to write out nice, neat, clean solutions to that. You can either print the page and write them on the page, or just write them on blank paper. But do me a favor and make sure you're writing one problem per page, and then scan it, get it all into one nice PDF, and upload those solutions to Canvas no later than the day of your final. We all comfy with where we're going and what's expected? Any questions?
Are you still gonna give us a study guide for the final?
That's right. No, I haven't put that together. I do remember you guys indicating that you would like something like that. I have a few more fires to put out regarding online testing right now, but I will put a little bit more time into study guide for you guys today. I know your final is coming up quick, so I will try to get that posted today. Yes. Any other questions? All right, then I will go ahead and end the meeting there. If there is anything that you want to talk about, please don't be shy. Just send me a Canvas message, and we'll get everything sorted out. I don't want anybody worrying or panicking or uncertain as to what's going on or what's expected of you as the semester wraps up. So if there's anything like that, please send me a Canvas message, and we'll get it all sorted out. Okay?
Actually, wait, real quick.
Sure.
What is tomorrow your last office hours as well?
Mm-hmm. Well,
Okay.
why not? Yeah, I'll keep my office hours through next week, and if you want to talk to me a little bit more, just send me a Canvas message, and we can arrange a separate office hour. So my other classes have
Okay, cool.
all the way through the 30th, which is next Thursday. So I'll have my normal office hours on the 28th and the 30th. And then if you want to talk a little bit more, we certainly could do that too. We could arrange an office hour for Friday or Saturday, Sunday, Monday, anytime between now and the final. I'd be happy to.
Okay, thank you.
Of course, of course. Anything else, guys? Okay, then I'm going to go ahead and end the meeting. If you do need to talk to me about anything, just send me a Canvas message. We can arrange an office hour, or we can talk through email, whatever you like. Okay, just don't suffer in silence. If you're worried about something, please ask. All right, have a nice morning.